Hi everyone, my name is Rogerio, and this is my presentation for IROS 2020 called Learning Visuomotor Policies for Air Navigation Using Cross-modal Representations. And this is joint work between Carnegie Mellon and Microsoft. So we humans are especially good at learning visuomotor policies, which are policies that map images as inputs to velocity commands as outputs. And we do this every day, for example, when we are walking around and avoiding obstacles on the floor based on what we see. And we can actually do this with a quite surprising degree of accuracy, even for controlling external bodies. So within a few hours of training, a human can learn how to fly a drone with quite surprising accuracy. And we can do this despite a quite challenging visual feed as input. We have very noisy images usually in FPV drone racing. And we can do this even among quite complex obstacle settings. And the overarching goal for this work is, can we teach a robot how to fly as well or perhaps even better than a human pilot? So in order for us to train these visuomotor policies for autonomous vehicles, we usually employ simulators. And simulators can be quite advantageous because they're quick, safe, and cheap for us to generate training data in. But a big problem arises when we have to transfer the policies that we learn in simulation to the real world. Because in real world environments, the appearances and the physics models that are involved are usually different than what you find in simulation. This is going to happen even if you use the best simulators out there. And a question that arises is, so why can we not just simply train all the policies in the real world directly? And the issue is that training with real world data is expensive, time consuming, and often dangerous when you employ real robots. We find very interesting works in literature that address this gap between simulation and reality. First, we find works that actually train visuomotor policies using only real world data, but they have efficient and safe schemes to obtain this data in real life. We also find work that train first in simulation and then they fine-tune some of the layers of the networks in real life. And we actually find a third category of works that train purely on simulation, but they employ a technique called domain randomization to randomize textures, appearances, and colors of objects and of the backgrounds so that the policy won't be confused when faced with real-world appearances. And a fourth category of works uses adversarial methods to try to make the policies not be able to discriminate between features coming from real world or from simulated data. Our approach, however, is a little bit different. Instead of treating the visuomotor policy as a black box between the image input and the velocity output for the drone, we actually break it down into a few components. First, we have a feature encoder, which compresses the input image into a latent state representation, and then we have a control policy that maps this representation into a velocity output. And something very important is that we enforce this latent representation to be trained only on simulation, but we make sure that it also generalizes to real-world data. And then once we fix the representation part, we train the control policy by using imitation learning, where we follow an expert controller that has the full state of the simulator. And by employing this two-step process, we can actually train a policy purely on simulation and then transfer this behavior to a real-life vehicle. So in this video at the bottom, you're seeing the behavior of our drone in real life that is employing a policy that was trained only on simulation. So now I'll give some more details on how we can learn compressed state representations for our task. It can be quite useful to use variational auto encoders to learn a compressed representation of the input image by first applying the image through a encoder network, obtaining a latent variable z, and then decoding this network and training the process using a unsupervised loss over the RGB space. But a big issue with these types of features is that they don't necessarily encode the information that is relevant for our task in hand. So they're encoding features of the RGB space, but not necessarily features that are relevant for the navigation task. The way we ensure that our latent representation contains useful features for our task in hand is by employing a technique called Cross-modal VAE, where we use multiple modalities of data at the same time to train a single joint latent space. So let's take a look at an example of what that means. Let's say we have a little robot that is delivering goods on a sidewalk, and we can capture multiple data modalities for this robot. Let's say images that it's taking, GPS locations of the robot itself and obstacles nearby, and also sounds of the environment around it. And we can train a single joint latent space by encoding these different data modalities in separate networks, and then by decoding this single joint latent space back into the original modalities. And the way we train these networks is by employing a round-robin fashion, where we have a single modality as input at a time, and then we decode the same latent space into multiple data modalities together. And what's interesting about this method is that we make sure that we have a lot of information encoded in this variable, and also by employing multiple modalities at the same time, we are implicitly regularizing the representation model so that it's much more robust to variations. And that's the trick that we employ to be able to train our models in simulation and then deploy them in real life, where you have differences in appearances. In the context of our application for drone racing, this means that we employ the cross-modal VAE to capture not only features of the RGB space with a unsupervised image reconstruction loss, but we have a separate decoder network that captures features relative to the position of gates in the environment relative to the drone's position. And we train these features by using a supervised loss because in the simulator, we do know where all the gates are and we do know the drone's position at every moment of time. This means that each point of the latent space contains a lot of information that is relevant for our task and is robust to appearance changes as well. We can actually take a walk over the latent space and see exactly what's being compressed into our latent representation. So here we're displaying the 10 variables that our vector Z contains, and we're showing different values for each one of those variables independently. And what's interesting is that by training this cross-modal variational auto encoder, we find that we created interpretable and even disentangled features. So you can see, for example, for the first 4 features, they actually are completely tied. They are tied to physical attributes of the scene. So the first one is related to the distance of the gate to the drone. The second one contains information about the horizontal position of the gate in the image. The third one is the vertical position of the gate in the image. The fourth is the rotation. The rest of the features are related to attributes in the RGB space. We also show in the paper that we found a smooth and continuous latent space. So here you can see an interpolation between 2 real images, image A and image B, that were captured by our drone, and we're drawing samples that are linearly interpolated on the latent space. And we decode these samples both in terms of image output and also in terms of the relative position of the gate to the drone for each one of those imaginary images. So on the top, everything you see, so the 2 images on the extremes are the 2 real-life images. Everything you see in between are imaginary images that were interpolated on the latent space. And we also see that the interpolation in terms of the, let's say, distance to gate or all the angles of the gate relative to the drone are quite smooth as well. We provide several ablations in the paper where we compare the performance of our Visuomotor policies in comparison with other baselines, such as end-to-end learning, and also using a conventional VAE that only cares about RGB feature extraction. And we can see that as the complexity of the track increases, our method is the only one able to keep racing, even under complex conditions. Here we can see another video where we show a quite extreme type of track and where our drone can still keep racing with good performance. We also provide quantitative results in simulation where we show that our methods are the only ones able to sustain good performance despite increased complexity in the tracks. And what's most interesting is that using our feature extraction method, we're able to train a policy only on simulation and deploy the same policy in quite challenging real-life environments. So you can see at the top, for example, we're flying the drone under quite heavy snowfall, so the appearances that we're seeing are quite different from what we trained on in simulations. We also deployed the drone in quite strong windy scenarios where the gates were shaking and moving all the time. And at the bottom right, you can see a top view of how the drone was flying in the circle among snow. In addition to the simulation experiments, we also have several ablations where we compare the performance of policies which were trained only on simulation and deployed in real-world environments. As you can see on the left side of the slide, we have two types of tracks. The first one is a circular track on line A, and then on line B we have a S-shaped track. Then on the right side of the slide you can see a table that contains the performance output of each one of the networks. So on the first line we have the cross-modal VAE, which significantly outperforms the other baselines. So on the S-shaped track, which contained 8 gates in sequence, we can go through the 8 gates in almost every single trial we've had. And then on the circular track, in our best trial, we're actually able to go through 26 gates in sequence without hitting anything, which means that we did over 3 laps with perfect performance. And for example, on the third line, we have a method that did quite well in simulation, where we were using as feature the estimated pose of the gates relative to our aircraft. But when you deploy this method in real life, it actually does quite poorly. Here we provide a visualization comparing our cross-modal method for feature extraction versus directly regressing to the gate of the pose next in front of the drone. And even though both methods were trained only using simulated data, you can see how by employing multiple modalities of data and implicitly regularizing our representation model, we're able to get a much better pose estimate of the gate relative to the drone, where we have less bias and also less variance in comparison to a method that only tries to estimate the pose of the gate using regression. We also provide a visualization of how our latent space looks over an extended period of time. So in this case, the drone is going on a circular track, and on the top right corner, we have the first-person view camera. So that's the RGB camera, that's the input to our system. On the bottom right corner, we're plotting the decoded gate position from our latent space. And in the center image, we can see we plot the estimated position of the gate on space in front of the drone. Here we provide a similar visualization, but for the S-shaped track. And in this case, we are actually maintaining the record of the plotted decoded positions of the gate in the map. And what's interesting is that the perceived decoded positions of the gates do resemble the actual shape of the track in a S-shaped curve. In the paper, we also provide experiments where we deploy the policies in quite challenging environments that have appearances that do not resemble at all the appearances of the environments that were used for training in simulation. So you can see this case where we have the drone being deployed on this abandoned swimming pool. So there's a big background color mismatch because the bottom of the pool is blue, which is not green like the soccer field that we used for training. We have quite big visual distractors like the red stripes at the bottom of the pool. And we have a big brightness contrast coming from the windows on the right side. And despite all these differences and challenging settings, our drone was actually was able to perform quite reasonably well in this environment. So in conclusion, over the course of this talk, we introduced the use of a cross-modal VAE framework that is able to jointly encode both raw sensor information in the form of images and also task-specific information into a single joint latent space representation. We also show that this representation significantly improves the navigation policy for our Visuomotor policies, both in simulation and also in real-life experience. And we also provided experiments that show that our policies are robust to environmental appearances that we see in real life and also to visual distractors. Finally, as future work, I'm really excited to try these cross-modal representations into new domains, such as ground vehicle navigation and also robotic manipulation, because those are domains that also count with pretty good simulators. And something else that I'm really excited to try is to explore different data modalities beyond images and poses. So for example, can we include sounds, depth images, and even LiDAR point clouds as different modalities which are encoded into a single joint latent space? With that, I conclude my talk, and I want to thank you all for listening. And if you're interested in more details, please visit our webpage where we have open sourced all the models and environments that we used throughout this project. Thank you.